Welcome to the second part of section 6.2. We want to talk today about line integrals of vector fields along curves. So let me remind you of what we did last time. We integrated a scalar valued function along a curve C using this formula. So the acronym was PEACE: parameterize, compute, and evaluate. So now today what we're going to do is look at what we do when we have a vector field and we want to compute the line integral of the vector field along the curve. And so I have a new set of formulas, which I'm going to talk about below, but here are the formulas here. Most often you're going to be asked for the formula in this form or this form. And then this one is the one you're actually going to use to compute because it tells you exactly what to do. So let's just do a quick review of the first type of line integral so that you can compare and contrast as we move forward today. One interpretation of computing a scalar valued function line integral, it's a mouthful there, is to compute the area of either a wall or last time I called it a curtain underneath the function and over the curve. So here we want to just set up the line integral. Our function is x plus y, and our curve is a piece of the parabola from 1, 1 to 2, 4, y equals x squared. So step one, parameterize. This is a curve y equals f of x. And so we can parameterize from our Bible by letting x be t and then y be f of t. So that's the Bible. And then we go from a to b, 1 to 2. So I'll let you compute r prime and the length of r prime and f of r of t. Well, I'll do f of r of t with you. Remember what you do. F is x plus y. You look at your parameterization. X is t, y is t squared. So f of r of t is going to be t plus t squared. And then in the formula here, you see this is my f of r of t. You can verify that this is the length of r prime of t, and I multiply, and notice you need parentheses there, multiply and integrate from 1 to 2. Now, if you actually had to do this integral, you would rewrite it as two integrals. One would be easy. The one with a t times the square root would be a straightforward u sub, and then the t squared times the square root would take a trig sub, not quite as easy. All right, so now let's look at vector fields and computing the line integral of a vector field along a curve. So for the application, I'm going to picture Florence, the goat, and she's moving. The wind is our vector field. Just imagine, wind is pushing her along the curve. How much work does that wind do to move her along the curve from A to B? Well, if we look at the dot product, F dot T, that gives us the work for a unit distance. Remember, t is a unit tangent vector. And so then if I multiply by delta s, that's arc length. I get the actual work done to move her that distance. So f dot t times delta s. And so what you see here is just a derivation of the formulas on the next page in the box. It's a little confusing because you can be asked for the same thing many different ways. The line integral of a vector field along a curve. Most often you'll be asked to compute this, or line 3, the integral over c of f dot dr. Those are the same thing. The one you're going to want to use to actually compute those is the one in red because it's the most informative. But you could also be asked, instead of just, someone saying, here's compute that number for this vector field in this curve, you could be asked to compute the work done by the vector field over C or the flow or circulation. These are all synonymous calculations. So line integral of a vector field, work, flow, or circulation. They're all pretty much the same. I'll talk about the difference between flow and circulation when we get there, but the formula for all of those things is this formula here. Okay, so keeping in mind that integral, let's call it work, the work integral is defined in terms of the dot product between the vector field and the tangent of the curve, unit tangent. We can estimate the sign of a line integral when we look at the vector field and the curve. So remember, if two vectors have an angle theta, then the dot product, u dot v, is going to be positive if theta is between 0 and 90. So I'll just say less than 90 degrees. And it's going to be negative if theta is between pi and pi over 2. I'll just say greater than 90 degrees. So in this first picture of Lutyens, here's some tangent vectors on that curve. They're all pointing in basically the same direction as the vector field. So the work here is going to be positive when I compute that number, since in each case, f dot t is going to be a positive number. Now, look at the same curve, but go backwards. So negative c means reverse orientation. Now my tangent vectors are going in the opposite direction, or theta, the angle between them, is going to be greater than 90 degrees. So the work here is going to be negative because I'm moving against the flow of the vector field. Now that's interesting because we know for a scalar valued line integral, so on this first page, going back up to the one we did last time, this number here, this was independent of parameterization. So when you go f ds over c, that's going to be the same number as negative c f ds. Reversing orientation doesn't change the area of the curtain, thinking of it like that. But reversing orientation will change the work from a plus to a minus. Okay, and so now we're looking at Florence, moving on this one. This to me would give us a work equals 0 because in each case, our tangent vectors are completely orthogonal to our vector field vectors. And then this last one's got kind of a combination, but for the most part, Florence is moving in the direction of the vector field. So I'd give that one a positive. Okay, so now let's do some concrete examples. Here's Lucian's, and she's being moved by this vector field along a parabola y equals x squared. So this is the same parabola as we saw in the setup on page 1, exact same parabola as we had here, but now instead of a scalar valued function that I'm integrating a vector field. So before it was x plus y, and now it's the vector field y comma x. And I've used technology to graph what that vector field looks like, and then I've superimposed the curve and Florence, sorry, that's Lucian's, so we can see that we should get a positive number. Okay, so we have to parameterize. R of t is same as on the first page, t comma t squared. T goes between 1 and 2. Now we need to compute. We're going to need r prime. That's 1 comma 2t. We don't have to find the length of r prime because looking at my formula up here, there's no length of r prime there. So I can stop at finding r prime. Still on the compute stage here, we've got r prime. We need f of r of t. All right, so we look at the vector field. It's y comma x. And then we go to our parameterization. X is t, y is t squared. So this will be y, which is t squared, comma x, which is t. So when you compute f of r of t, you're getting a vector. Whereas when you compute a scalar valued function, like on the first page where our f was x plus y, then when we computed f of r of t, we got a single function. We had t plus t squared. So function, vector, that's the difference. Then we're going to need to compute the dot product of f of r of t and r prime of t. F of r of t dot r prime is t squared comma t dot r prime is 1 comma 2t, and I get t squared plus 2t squared is 3t squared. Step 3, evaluate. So work is the integral from 1 to 2 of 3t squared dt, which is very nice to work out. This is just t cubed between 1 and 2. 2 cubed is 8. 8 minus 1 is 7. There's the work. Let's look at another example. I'm trying to mix up the notations for you. Here we're just told to evaluate this line integral, and that's synonymous with saying find the work done by this vector field along this curve. So we're going to use the exact same formula right here in the red box. So step 1 is done for us. The parameterization is cos t sine t. T goes from 0 to pi over 2. So this is our x and this is our y. Step 2 is negative sine t, comma, cosine t. F of r of t is, f is x squared, so that's cosine squared t, comma, negative xy, cos t sine t. So the dot product, f dot r prime, cosine squared t, comma, negative cos t sine t dot negative sine t cosine t is going to be negative sine t cosine squared and then minus sine t cosine squared. So that's negative 2 cosine squared sine t. I reversed the order between cosine squared and sine. I don't know why. The order does not matter. So step 3, the integral over c of f dot dr is the integral from a to b. My a is 0 and my b is pi over 2. Those come from the parameterization. And I'm integrating negative 2 to cosine squared t sine t dt. All right, so I'm going to let u be cosine t. du is negative sine t dt. That's nice. So we pick up that minus sign. So this is going to be the integral of, the minus is taken care of, 2 u squared du. And my limits are cosine of 0 is 1 and cosine of pi over 2 is 0. So if you wanted, if that bothers you to have the upper limit less than the lower limit, you can flip these, but then you introduce a minus sign. I'm just going to integrate it the way it is. It doesn't bother me to have that order right there. So when I integrate, I get 2/3 u cubed between 0 and 1. So just be careful that you do the order right. You're going to get 0 minus 2/3. That's a 2/3, which is negative 2/3. Okay, flow and circulation. So if we imagine the vector field being current or some sort of fluid moving along, then instead of saying this line integral is the work, we call it the flow. And because what we're doing is computing how much liquid is flowing around that curve when we do f dot t. Now this is also called the circulation if c is a closed curve. So if you go all the way around a closed curve, we call it the circulation. Otherwise, we call it the flow. Some people use them synonymously, but I think it's pretty common to restrict circulation to a closed curve. So let's look at a couple of examples. Find the circulation of the field around the circle cos t sine t. And I have two separate examples. By the way, I should mention before I move on, the flux. So flow measures how much fluid goes around the curve, whereas flux measures how much fluid or whatever it is, gas, goes through the curve. I haven't assigned any flux problems. It's a different formula. And so I'm just going to stick to flow and circulation for this section. I think you're going to have your hands full. In the homework, what I've done is I've jumbled up all your problems. So don't expect all the problems in section 6.2 part 2 to be vector field problems. I've thrown in some scalar valued line integrals and some line integrals of the old type not old type because it came from last time, f dx or f dy, or a combination of f dx plus g dy. And so then you also have some f ds's, and then you also have some big F dot dr. So there's a jumble of stuff and you have to use the correct formula. All right, our parameterization is done for us in each case. So this is x, this is y. We're going to need r prime of t, and that's negative sine t cosine t. We're going to need f of r of t. Now in this first example, our vector field is x comma y. So x is cos t, y is sine t. So f dot r prime dot this vector with this one, and we get negative sine t cos t plus sine t cos t, which is 0. So our flow, I'll just call it big F. Oh no, that's confusing because that looks like the vector field. I'll just say the flow, or the circulation. Since this is a closed curve, we can call it circulation, but I'm going to call it flow, is the integral from a to b, 0 to 2 pi, of 0 dt, which is 0. And we see that our tangent vectors are always orthogonal to our vector field vectors, and so we're not surprised to get 0 for flow. And we won't be surprised in the next picture if we get a positive flow, because it certainly looks like our vector field is going along with the tangent vectors to the curve. So again, the parameterization's done. It's the same as before, x, y. R prime is the same as before, but I'll copy it down again. Negative sine t cos t. F of r of t, negative y. So y is sine t, negative sine t. And then x is cos t. So f dot r prime is positive sine squared, because you have a negative and a negative. So sine squared t plus cos t times cos t is cosine squared t. That's 1. So our flow, or our circulation, or just the integral over c of f dot dr, is the integral from 0 to 2 pi of 1 dt. And so that's t between 0 and 2 pi, which is 2 pi. Okay, so that is it for this section, and there are no practice problems for you to do, unfortunately. So you can just jump into your homework after you're done with these lecture notes.